describe where electrons are in atoms. So, describing their location in an atom. Okay, and so this last one is quantum numbers. And I have in parentheses electron addresses. And you guys, this is kind of like a code. Now, I can't remember in your book. I think in your book this comes first. Quantum numbers, and then electron configurations, and then orbital diagrams. I think that this is the most abstract. And so that's why I've saved this for the last. Even though in terms of chronological order, when these ideas first came to light, this probably is first. And you'll see why here. Okay. Yeah, here we go. Let's write a book. In 1926, Schrodinger formulated an equation that describes the behaviors and energies of submicroscopic particles in general. It incorporates both particle behavior in terms of mass and wave behavior in terms of wave function. Okay, so again, Schrodinger's model of the atom incorporates both particle and wave nature of where we're concerned here of electrons. And then in terms of orbitals, that electrons occupy areas that are in the same shape as the wave function that they are behaving, the wave they are behaving like. Okay. I probably just butchered that terribly. Alright, now derivations of Schrodinger's equation gives us three different quantum numbers. The principal quantum number, the angular momentum, and the magnetic quantum number. These three are used to describe orbitals and label electrons. Okay, so really you guys, this idea came first, and it came out of Schrodinger's equation in terms of how to describe an electron. So remember, Schrodinger's idea of the atom, electrons behaving like or we think of electrons as a cloud of negative charge. They're behaving like a wave. Okay, this is the most evolved idea of the atom at this point. And from that equation, we get these descriptions of electrons. And not of the electron itself, but where the electron is in the atom. The location of the electron in the atom. Or not its location. It's the region where the electron might be. Okay. Because we can't ever pinpoint it exactly. It's like you. You know, at any given point in time, let's say even when you're in class. Okay, and it's the time when you are in this classroom. We can tell somebody the address of the school, and we can give the classroom number that you're supposed to be in at that particular time. I could even produce a seating chart and say this is where this person is probably going to be at this point in time. But are you always in that spot at a given point in time? No, you might be up to sharpen your pencil, you may have gotten up to throw something away. And so you just can't ever exactly pinpoint where the darn electron is going to be. You can describe the area. Okay, so fourth quantum number spin describes the behavior of a specific electron. Okay, so number one, the principal quantum number. Okay, you guys, this is a code. and it is represented by N. So this doesn't mean number of moles. This means the distance that the electron is from the nucleus. N equals 1. That means quantum level 1. N equals 2. Quantum level 2. So this relates to the average distance of the electron from the nucleus. The larger the N, the further from the nucleus. So, principal quantum number, abbreviated as N, code is N, and it's telling us the distance from the nucleus, what energy level that electron is residing in. Principal energy level. All right, number 2 is angular momentum. And that is abbreviated as this cursive L. This tells us the shape of the orbital. So in quantum number code, if L is equal to 0, that means that the electron is in an s orbital. If L is equal to 1, that means that the electron is in a p orbital. If L is equal to 2, that means that it's in a d orbital. And if L is equal to 3, that means that that electron, that particular electron, is in an f orbital. All right, you guys, this lecture is bad enough face-to-face. I'm going to have to do a lot of teaching about this in class because I know that this isn't going to do it, but at least you're going to have the notes. All right, number 3, the third quantum number represents, so we abbreviate this as m sub L. And this describes the orbital orientation in space. Oh boy. Okay, so I've got a lot of things written here. So, 2p. There are always, if a quantum level has p orbitals, it always has 3 p orbitals. P sub x, p sub y, p sub z. And so, if the third quantum number has a value of -1, that means that we are talking about the p sub x orbital. X, y, z, in terms of the orientation in space of the p orbitals. If the m sub L has a value of 0, that means that it's the p sub y orbital. And if the value is 1, it is the p sub z. Now, s orbitals, well, if a quantum level has, as they all have, an s orbital, there's only one of them. So, the m sub L code for an s orbital is going to be 0. If a level, quantum level, has d orbitals, it's got 5 of them, and the codes for those are going to be -2, -1, 0, 1, and 2. And again, they denote the orientation in space. And the easiest way to think of that, you guys, is x, y, z, but these are more complex. F, if there are f orbitals, there's 7 of them. -3, -2, -1, 0, 1, 2, and 3, 7 of them. Okay. And finally, electron spin. It's the fourth quantum number, m sub s. Each electron in an orbital has a distinct spin. We describe those as the easiest way as being clockwise or counterclockwise. And so the numbers for those are +1/2 and -1/2. And so, definitely not doing the next thing here. What does a set of quantum numbers look like? What does this code look like? Every electron has its own set of 4 quantum numbers. And so you guys, let's go ahead and write the quantum numbers associated with a hydrogen electron. Okay, so hydrogen has a single electron. Where does that electron reside? Well, it's a 1s morph, right? So it's got one electron at quantum level 1 in the s orbital. Okay, how can I use quantum numbers to describe that? Okay, so we're going to say n L, m sub L, and m sub s. Okay, n describes for us the distance from the nucleus, the principal quantum number. What is the principal quantum number for this electron? Well, it's in quantum level 1. Okay, L is the code for the shape of the orbital. Okay, this electron is in an s orbital, and so what is our code for an s orbital? Let's go back to our notes, and what that tells us, you guys, is that s is 0. Now, because there's only a single s orbital, there's no x, y, and z, right? So there's no 3 orientations in space. It's just spherical. All right, what is our code for simply spherical? It is 0. And last but not least, by convention, you guys, we say that the first electron in an orbital has a +1/2 spin. What does our orbital diagram for this look like? 1s, looks like that. There's our orbital diagram that describes that electron in hydrogen. Here is the electron configuration that describes the location of that electron. And here we have the set of 4 quantum numbers. Those 4 quantum numbers also describe the location of that electron in the hydrogen atom. Quantum level 1, S-shaped orbital. There is only one orientation in space. We don't have to say piece of X, piece of Y, piece of Z, etc., right? So it's 0, and then by convention, the first electron has +1/2 spin. Now, if we did this for helium, right, there's its electron configuration. There's its orbital diagram. Now, each electron has its own set of quantum numbers. So if we want to describe both of the electrons in helium, we have to write a set of 4 quantum numbers for each of the electrons. Now, of course, the first electron is going to be identical to this one, right? It's going to be 1, 0, 0, positive 1/2. That's this electron right here. How do I describe this one? I should have color-coded that. Would have made it a little bit easier, but okay. How do I describe this one? This is the description for this electron. What's the only difference between this one and this one? It's still in quantum level 1. It's still in an s orbital. There's only one orientation. The difference is going to be what? The spin. And so it's going to be negative 1/2. Lithium has 3 electrons. So if we want to describe all the lithium, all the electrons in lithium, according to quantum numbers, right, we're going to